In this video, we're going to take a look at our first analytic sort of pencil and paper approach to actually solving differential equations. And we're going to focus on a type of a differential equation called a separable equation. And we'll talk about what that means in just a minute. But let's go back to kind of the big picture. Previously, we said that when we're solving a differential equation, or just solving an equation in general, it requires undoing whatever operations were done in order to create that equation. And so in the context of a differential equation, one of the main operations that we need to undo is the derivative that shows up within the differential equation. How do we undo a derivative? We undo a derivative via integration. So to solve a differential equation, we'll need to undo that differentiation. And again, we undo that derivative with integration. So let's take a look at an example. Consider the following. What if we'd start with a relatively simple equation here? I'm just going to pick dy dx equals y. So I've got my equation. It's a differential equation because we have the derivative, and I need to undo the derivative so that we can solve for y. So can we just integrate both sides of this with respect to x? By integrating this side, I could undo the derivative. So can we simply integrate both sides? And in this case, with respect to our independent variable, which happens to be x. And again, WRT means with respect to. So can we integrate both sides with respect to x? Turns out the answer to that is, unfortunately, no. And we'll see what happens if we were to just try it. So let's naively just say, okay, let's integrate both sides. So what we'd do is we'd start by integrating the dy dx term with respect to x. And we'd also have to do the same thing to the other side. So integrate y with respect to x. So I basically introduced the integral symbol to both sides, and I've had to introduce a dx to both sides so that we have, so it's clear which variable we are integrating with respect to. And on the left, this is nice. This dx and this dx actually cancel out, and we just have the integral of dy. And let me just concentrate on the left-hand side for now, so I'll just copy the right-hand side down. And when I integrate dy, I will simply get y plus some constant of integration, and that's equal to the integral of y dx. So how do I integrate the right-hand side? We've taken care of the left-hand side, we've solved for y. How do I deal with the right-hand side? Well, unfortunately, we can't deal with the right-hand side because y is the unknown that we're trying to solve for to begin with. This is some unknown function. I can't integrate it. It shows up over here as well. It's the thing that I'm trying to solve for. So what we've done is taken what was initially a differential equation, and we've turned it into something where now there's no derivatives in this equation, and instead there is an integral in this equation. So if I were to solve for y by moving that c over to the other side, and I guess technically it would be minus that particular constant c, or plus some other constant c, doesn't matter. We come up with an equation like this. And it turns out this thing is called an integral equation. And they're even more of a pain in the ass to solve than a differential equation. So this is an integral equation. It's worse than a differential equation. And so we haven't really made any progress. In fact, we've made things worse. Okay, so that's not going to work. We can't just naively integrate both sides. So how do we solve a differential equation of this particular form? Well, it turns out if we do a little bit of algebra first, then we are going to be able to integrate both sides. but I need to kind of group all the y terms together and all the x terms together. So how can we proceed? Let's do a bit of algebra. So what I'm going to do is I'm going to go back to our original equation, dy dx equals y, and I'm going to isolate all the y's together on one side of the equal sign and all the x's on the other side. And so in this particular case, what that means is, let's say I want to keep the y's on the left-hand side. So I have the dy on the left-hand side already, but I have y on the right-hand side. How do I get rid of the y on the right-hand side? I need to divide both sides by y. So if I divide both sides by y, I'll have dy over y dx is equal to just 1 because we divided the right-hand side by y. Now I've got all the variables on the left-hand side. It's good, I've got all the y's where I need them to be, but I also have an x over here. And so I want to get rid of that x. How do I get rid of the dx that's in the denominator here? Well, I need to multiply both sides by dx. And when I do that, I'll wind up with dy over y is equal to dx. And now I'm going to have the ability to actually integrate both sides without any issues because I didn't have to artificially introduce the differential dx. I've already got the y's grouped together. I can integrate the left-hand side with respect to y. The problem wasn't integrating y in general. The problem was integrating y with respect to x. It's an unknown function of x. But I can integrate y with respect to itself because that's an easy thing to do. You can integrate any variable or function of a variable with respect to that same variable. So in this case, now we can integrate both sides. And when we do that, I'll have on the left-hand side the integral of dy over y, and on the right-hand side I'll have the integral of simply dx. How do we integrate the left-hand side? Well, I basically have a function that looks like 1 over y that I'm integrating with respect to dy. What's the integral of 1 over y? Or if you're more used to integrating functions of x, what's the integral of 1 over x? It's a natural log. So whenever you have 1 over that variable and you integrate it with respect to that same variable, you're going to get natural log. So on the left-hand side, I'm going to get the natural log of the absolute value of y. And technically there's a plus c, but I'm also going to get a plus c when I integrate the right-hand side. So instead of having two different plus c's, one on each side, let's just do, if I get one constant on this side, a different constant on this side, I can always subtract the constant from the left over to the right, and I only have to write that constant in one place. So integrate the right-hand side. What's the integral of dx? It's simply x plus, here's our one constant that we have of integration. So here's what we get after we integrate both sides. And we're starting to get on our way. The problem is our initial equation was a differential equation where y clearly is our dependent variable, and ultimately y is the function that we want to solve for. So I need to solve for that down here. But we've done all the calculus. The rest of what we have to do is simply algebra. So solve for y now. How do I solve for y? Well, right now y is trapped within an absolute value sign, and it has a natural log being taken of it. So how do we undo the natural log? Undoing a natural log requires exponentiation. So if I take e to both sides, e to the natural log of the absolute value y is equal to e to the x plus c. I can cancel this e with this natural log and be left with simply on the left-hand side, simply the absolute value of y. And on the right-hand side, we can use our exponent rules. When we have a common base, e to the x plus c, or e to something plus another thing, I can rewrite that as the product of two separate exponentials. So I can rewrite this as the product of, in this case, e to the x times e to the c, or in this case, I'm going to switch the order and do e to the c times e to the x. Right? Whenever you have a product of two exponentials with the same base, you can add the exponents and get something equivalent. So we're basically kind of using that rule in reverse. I'm taking something where we've added the exponents and instead breaking that into two separate exponentials. The nice thing about this is that this e to the c is some unknown constant. We haven't picked what c is yet. And that means when I take e raised to some number, some unknown constant, I'm going to get some other new unknown constant. I can get more or less whatever I want to get out of this thing. So in this case, I'm going to rewrite this e to the c as some new constant. Maybe we call it c2, or maybe we call it k, or something else other than e to the c. So I'm going to choose to rewrite that as, let's call it c1 e to the x. And just to make it clear, c1 is equivalent to e to the original c that we had. So c1 is a different constant than c. In fact, c1 is what you would get if you take e and raise it to the power of that initial unknown constant c. Okay, the last thing we need to do is get rid of the absolute values. But we need to think about this just a little bit. If I come back to this c1 that we've written right here, I know that it's equivalent to e raised to the power c. What do I know about this number c1? What has to be true of this particular value, knowing that it can be written as an exponential e raised to some constant? Well, regardless of what I pick for c, be it a large positive number or a negative number or even 0, no matter what I pick, e raised to some number is always going to be positive, right? If I raise it to e to the 0th power, e raised to the 0th power is just 1, which is positive. If I pick c to be a large number, 100, e to the 100th power, that's some huge number. I don't even want to speculate what it is. Quintillions, gajillions, some giant number. And alternatively, if I make c negative, a negative number, e to the c, where c is some negative number, negative 10, well, that's the same as 1 over e to the positive 10, which is just 1 over some large number. And the whole thing is still positive. Close to 0, but positive. So at worst, basically, if c gets to be a really large negative number, c will approach 0, but it's still going to be positive. It's still going to be on the positive side of things. So let me just erase this, and hopefully that's convinced you. All I know is that this thing is definitely greater than 0. It's a positive number. And so if this number is positive, and we have e to the x, another exponential, which by the same argument that I just erased over here also needs to be positive, then we don't really need to worry about this absolute value symbol anymore. Basically, what we can say is that y must be equal to c1 e to the x. And let's call it, just to be clear, another way we could do it is say, let's say that, so another argument we could make is, let's say that the absolute values, if there were some way, hypothetically, that this could wind up being a negative number, and that would make this whole thing over here negative, and and it doesn't make any sense anymore. That's basically the argument that we just went through. But alternatively, you could think of it as we're just rolling the absolute value into the unknown constant, right? Get rid of the absolute value, and we'll just change what this constant could potentially be called. So either way, the second one's kind of a hand-wavy explanation. The first one's a little bit more rigorous. But the point at the end of the day is that this thing looks like y equals some constant times e to the x. And that's the solution to our original differential equation that we have right here. And aside from solving it the way that we did, another really good approach is to just come back and in retrospect, let's use some common sense. If I'm trying to solve the differential equation dy dx is equal to y, what I'm claiming is that there must be some function y, that original function is equivalent to what I get if I take the derivative of that function. So I'm looking for what is a function that stays the same when you take a derivative. What is a function that spits out itself as its own derivative? And what's the answer to that? Well, exponentials spit themselves out. In this case, e to the x. What's the derivative of e to the x? E to the x. And you can put any constant you want in front of that because that constant would survive the differentiation. I'd have that constant over here. I'd have the same constant on this side. And we would just have some constant times e to the x equals some constant times e to the x. The same function is equal to itself on both sides. So from a common sense standpoint, hopefully we could have anticipated by just looking at this and asking that question, what is a function that when you take its derivative, you get back the original function? And hopefully it's obvious that the answer to that is Well, that's what exponentials do, e to the x. And so that makes this make sense as well. So we've solved for it sort of in a rigorous way using what's called the separability of the equations. We separated the y variables onto one side, the x variables onto the other, and then integrated both sides. But we could also have anticipated that solution just via mathematical intuition at this point. Okay, so this method is going to be really, really nice and useful. We're going to be able to solve a lot of differential equations with this approach, including ones a lot more complicated than the one that we just looked at. So when will this work? So when will the separability work? When is a differential equation going to be separable? When can we isolate the x variables on one side and the y variable on the other side? And it turns out a differential equation is separable. So this is, in a sense, our definition of separability is separable whenever it takes the form of the following. Form, see if I can write form of dy dx equals some function of x times some other function of y. Because if I have something that looks like this, where I can explicitly factor the right-hand side into something that involves all the x variables times another thing that involves all the y variables, I can solve or separate the two variables by just multiplying both sides by dx and dividing both sides by h of y. So you could always separate it in the following way. We would always get dy over whatever the h of y is by dividing both sides by the h of y. And by multiplying both sides by dx, we would get the g of x to stay on the right-hand side times that dx. And now we have something that's strictly a function of y on the left and something that's strictly a function of x on the right. And we could integrate both sides. So this is the key. If you can write it like this, you have a separable equation. And so this is going to be a common approach. This is going to take care of a very wide array of problems that we're going to face, but certainly not all of them. So let's do another example and just get a little more practice with this. Let's say I want to solve, let's say dy dx, and again, we're sticking to only first order equations for the time being. So notice that this is only a first derivative. I'm not going to have any problems in chapter 2 here that involve second derivatives or higher derivatives. We'll start dealing with that in a later chapter. So for now, I have dy dx is equal to, let's say, x squared y. Easy enough. So if I got x squared y, we would separate everything. This is separable. Clearly, it takes this form. I have something that's strictly a function of x. So my g of x term is x squared. My h of y term is just y. And we can separate the equation by multiplying both sides by dx, dividing both sides by y. And so I'll get dy over y is equal to x squared dx. We will integrate both sides of this. And that will give me, if I integrate both sides, on the left, we'll get the same thing we got before, so this will be very common. See the natural log of the absolute value of y. And on the right-hand side, what's the integral of x squared? Well, it's going to be x cubed, and I need an extra factor of 1/3 x cubed to get that to work out. And we can't forget our plus c. Our plus c is incredibly, incredibly important in getting these to work the way that we want them to work. If we look back at this one here, the plus c term wound up being the constant that we had in front of the whole exponential. We'll see some cases where it's even more imperative than that. So what I'm trying to suggest is oftentimes the plus c is going to be, honestly, the most relevant part of what we get when we integrate both sides. It's going to lead to the most important parts of the equation. So do not forget your plus c. Okay, so same thing, let's solve for y. I'm going to solve for y by exponentiating both sides to get rid of the natural log. So I have e to the natural log of the absolute value of y is equal to e to the 1/3 x cubed plus c. Same argument as before. Maybe we can knock this out in a couple of steps here. So the e and the natural log will cancel, and I'll just be left with the absolute value of y on the left-hand side. And on the right-hand side, I'm just going to call this e to the c term some new constant. So let's just call it k again. I'm going to have k times e to the 1/3 x cubed. So again, just to be totally explicit, the k is equal to e to the c. And we know that that has to be positive, right? So k being equal to e to the c must be positive, so we can drop the absolute values. So let me write that as well. So drop the absolute values, and we're left with y equals k e to the 1/3 x cubed. And so there is our general solution to this differential equation. And if you want to verify whether something is indeed a solution, this is something that we kind of skipped. All you need to do is go plug this solution back into the original equation. So let's just check. Another way that you might see this phrased is verify. Verify that this solution is correct. So we have that y is equal to k times e to the 1/3 x cubed. We're also going to need, looking at our equation, we're also going to need dy dx. So what is dy dx? Well, I need to take the derivative. What is the derivative of this thing? So it's k. The k will survive our derivative, times the derivative of e to the 1/3 x cubed. So this is going to require us to do chain rule. It's basically the derivative of, and again, if you've taken calculus with me, this will sound familiar. If not, what I like to think about it when I do chain rule is I really want to think of this function as being e to some stuff, raised to the power of some stuff. There's some function up here. So I have k e to the stuff. What's the derivative of e to the stuff? E to the stuff. So what's the derivative of e to anything? E to that same thing. And then all I need to remember is that then I need to take the derivative of the stuff. So what's the derivative of that stuff? What's the derivative of the 1/3 x cubed? The 3 will come down and cancel with the 1/3. The power will drop by 1, and I will just get x squared. And so when we plug into our original differential equation, which looks like, see if I can get it all on the screen at once, which is dy dx equals x squared y, I'm going to plug in this for this particular y. I'm going to plug in this for dy dx, and on the left-hand side, I will get k e to the 1/3 x cubed times that factor of x squared. And on the right, I'll get x squared times the original y, so times k e to the 1/3 x cubed. And what do I see? They're in slightly different orders. Here the x squared shows up at the end, here the x squared shows up at the beginning, but these are exactly the same. So those two things are identically equal to one another. And we must have found the solution that solves the original differential equation. And again, what we found is what is called a general solution. The general solution is the one where we haven't plugged in a specific value of k yet. And so this goes back to the idea that I talked about when we mentioned initial value problems. Because we integrated and introduced this unknown constant of integration, if we want to get a unique solution, we need an additional piece of information to allow us to solve for the value of k. So I need to specify that maybe y of 0 is equal to 1. And if y of 0 is equal to 1, and I just pulled that out of thin air, there's nowhere that came from, but if y of 0 was equal to 1, so hypothetically, let's just do this over here. If there was an initial condition given that says y of 0 equals 1, all that means is that when I plug in x in place of the, or 0 in place of the x, it would spit out the value of 1 for y. And so I would plug that into the equation, and we'd get 1 on the left-hand side for the value of y, as long as I plug in x equals 0 on the right-hand side. So 1 equals k e to the 1/3 times 0 cubed. Well, 1/3 0 cubed is still 0. E to the 0 is just 1. And I would wind up with simply 1 equals k. And we would have found a specific value of k that will satisfy this particular initial condition. So this is how we will implement initial value problems. We will need one extra piece of information to solve for our one remaining unknown in our general solution. This is the idea, just to be totally clear. The general solution to a differential equation will always involve k or c or whatever you want to call the unknown. It'll always involve some unknown. But if you have the appropriate initial condition or initial conditions, depending on how many are required, for first order equations, it's only one that's required, one extra piece of information, you can solve for that particular value of k and wind up with what's known as the particular solution. So that's going to be the process. Hopefully that's clear. Let's just do maybe another example or two here. Just keep knocking these out. So in this example, I'm going to make it a little bit more complicated. I'm going to write this one as e to the x times y dy dx is equal to e to the negative y plus e to the negative 2x minus y. Okay, so right off the bat, this doesn't look like the general form that we needed. But part of that's because I have this term over here that's kind of stuck next to my dy dx term. So let's see if we can get rid of basically this piece over here and separate it out so the x's are all on one side of the equation, the y's are all on the other side. And so let's kind of just take a look and see if we can come up with some intuition that'll tell us what would be a good first step to take. If I just jumped straight into it and tried to basically multiply everything by e to the negative x to cancel out this term, and divide everything by y to cancel out this term and get this piece by itself, I'd get an even more hideous function over here on the right that then we'd have to do a bunch of algebra on to try to separate it out. So instead of just doing that and trying to isolate this piece by itself, I'm going to embrace the fact that there's already some terms kind of separated to each side. So for example, the dy over here on the left in the numerator, let's leave that there, and let's leave this y that's sitting next to it there as well. So I want to keep this y on this side, the dy on this side, and I want to move these other terms that involve y over to this side. As far as the x is concerned, right now it's in the denominator. I'd much rather move it up here to the numerator. In fact, we have to move it up to the numerator, so I'm going to multiply both sides by dx to get the x variables showing up on this side. I don't need to touch this term that involves x, the e to the negative 2x term. But I am going to need to move this one over to the other side. So I am going to ultimately multiply by e to the negative x to move this term over to the other side. So some other ways that we might have some intuition for that. Notice that on the right-hand side, both of the terms in the way that they involve y in the same way. I have an e to the negative y here, and you could think of this doing the same thing that we did before as being e to the negative 2x times e to the negative y. So really both of these terms involve an e to the negative y. And if I want to move that e to the negative y term over to the other side, and I want to cancel it on this side, I can multiply both sides by e to the positive y. So this is kind of the idea. I'm going to, let's multiply, and we're doing this to both sides, multiply both sides by, first things first, let's get this e to the x over to the other side. So I'm going to multiply both sides by e to the negative x to move that over to the other side. I'm going to multiply both sides by dx to move that over to the other side. And then I'm going to multiply both sides by e to the positive y to cancel out both this term and this term on this side and move it over to the other side. So e to the positive y. So if we combine these, we could really multiply by a single term that looks like e to the y minus x dx. And so let's just see what happens when we do that. And if you want, you could also just do it separately, one piece at a time. So it's really basically boils down to how comfortable you are with the algebra, but this is just an algebra problem so far. So if we want to do them in multiple steps, let's just do them separately. So instead of multiplying the whole thing by this, I'm going to do each one of these separately. So the first thing I'm going to do is multiply both sides by e to the negative x, and that would leave me with y dy dx on this side, and then on the other side I'll have e to the negative y plus e to the negative 2x minus y in parentheses times e to the negative x. Just make life a little bit easier. Next, let's multiply both sides by dx. So I'll have y times dy is equal to the same thing, e to the negative y plus e to the negative 2x minus y, e to the negative x, times dx. I've moved the dx out of the denominator here. It shows up in the numerator over on the other side. And then the last step is going to be moving this e to the y over to the other side, or these e to the negative y's rather, over to the other side. So to do that, first I'm going to factor this, and I'm also going to distribute this through. So I'm going to do a couple of steps of algebra here. So I'm not going to touch the left-hand side yet. First thing I'm going to do is see that I have an e to the negative y here. So let me rewrite this. This is e to the negative y plus, on this piece here, I could think of this as e to the negative y times e to the negative 2x. Right? Same rule that we used before to separate when you have a sum or difference of terms in the exponents. You can create that as a product of exponentials. And we have our e to the negative x dx that I haven't touched yet. And so now I can factor this e to the negative y out. I'll be left with 1 plus e to the negative 2x times e to the negative x dx times y dy. And we're getting really close. I'm going to multiply by e to the positive y to get rid of this y term. That's the last remaining y term on the right-hand side. So I'm going to have y e to the y dy is equal to, and now I'm just left with the 1 plus e to the negative 2x times e to the negative x. And if I distribute that through, let's knock that out as well. So I'll get an e to the negative x when I do this term times this term. And then when I do e to the negative 2x times e to the negative x, I can add exponents and get plus e to the negative 3x. And again, I've got my dx multiplying the whole thing. Okay, so there's just a bunch of algebra. This was all algebra. We have not done any calculus, any differential equations yet, just algebra. Okay, so however you want to do this algebra, here I did it sort of in a laborious step-by-step process. Alternatively, it would have been faster if we just jumped straight to this from the get-go. Whatever level of comfort you have with algebra, use that approach. Don't make stupid mistakes on the algebra. It tends to be one of the biggest things that people screw up on in this class, and it has a terrible cascading effect where making a tiny mistake early on in the algebra makes the rest of the problem oftentimes basically impossible to solve. So don't make silly algebra mistakes. Be methodical, be careful with your algebra. Okay, so I finally got it set up down here where I've separated all the y's on the left, all the x's on the right, and we are at the point that we can integrate both sides. So let's integrate both sides of this equation. On the left, I'm going to need to integrate by parts. So we're going to need to be comfortable with all those integration techniques that you learned back in the tail end of Calc 1 and the early parts of Calc 2. Here I have a function times another function. This is one that I recognize as integration by parts. Over here, this one's not so bad. I can just split it up into two separate integrals. I'll have the integral of e to the negative x dx plus the integral of e to the negative 3x dx. This one technically requires a u substitution, but it's one that I can more or less do in my head. So I'm not going to worry about the right-hand side too much. Let's focus on this side. So this side I'm going to integrate by parts. And this side is not too bad. So for now, I'm going to focus on the left-hand side. I'm going to let my u and my v, my u and my dv be two functions, and then I'll get du and v as the two remaining pieces. So what should I make what? and because it's probably been a while since you've been doing these, let me give you a reminder of the way that I like to approach them. In general, I want to set u to be whatever function gets simpler as we take derivatives. So if it's possible, if you have one of the two parts, in this case we've got a y and an e to the y, if one of them gets simpler as you take derivatives, and in this case that's going to be the y, because when I take the derivative I'll just wind up with 1, or just with dy rather, pick that part to be your u. And if you have something that's easy to integrate, or something that integrates cyclically, and by cyclically I mean as you integrate it over and over, you kind of get repetition, so things like exponentials, sines, and cosines, things of that nature, pick that to be the part that you integrate. So in this case, I'm going to pick u to be the y, the dv is going to be e to the y dy. This is easy to integrate. The integral of e to the y is also e to the y. And over here, when I take the derivative of y, I'm just going to get 1. So 1 times dy. So here are the values that I've picked. And that's going to give me, for the left-hand side, I'm going to get uv, so y e to the y, minus the integral of v du. So e to the y dy. And that's going to be equal to the right-hand side, which I haven't touched yet, so let me just copy it down. In fact, let me break it up into the two separate integrals. So integral of e to the negative x dx plus the integral of e to the negative 3x dx. So I haven't touched this side yet, other than splitting it up into two separate integrals instead of being written as one integral. But this side is easy. From here, I'm going to get y e to the y, and what's the integral of e to the y dy? That's just going to be another e to the y. And on the right-hand side, let me make it totally explicit that we're going to also have a plus c here. And it can come from, you can think of it as coming from the integrals that we did on the left, or the ones on the right, or all of them combined, but we need to be explicit. There is going to be a plus c when it's all said and done. So now let's integrate these. These are both going to technically require u substitutions, but hopefully you've gotten to the point that some of these can be done in the head. So what is the integral of e to the negative x? Well, it's definitely going to be something that involves an e to the negative x, and all I need to do is make sure that when I take the derivative of e to the negative x, I get the appropriate sign. So what's the derivative of e to the negative x? Well, I'll get e to the negative x times an extra factor of negative 1 from the chain rule here that I don't have here. So to make up for that, let's put a negative sign there. This is the correct integral of this. I anticipate that negative sign here, which will counteract the negative sign I'll pick up by chain rule when I take the derivative of the e to the negative x. And that'll give me the e to the negative x that I want. So basically, for me, integration is hard. Differentiation is much, much easier for me. So I basically treat a lot of these simple u substitution problems as though they were differentiation problems. I kind of guess what the function is going to be. I know it's going to be e to the negative x with something out front, and then I take the derivative and kind of thinking backwards to figure out what that correction factor has to be. So same thing over here. I know that when I take the derivative of e to the negative 3x, I'll get back the e to the negative 3x that I want here. But I'm also going to pick up an extra factor in that case of a negative 3 that I do not want to have, because there is no extra negative 3 that shows up here. So to account for that, I'll put a negative 1/3 out in front of everything. And there is the solution so far. So one thing that I want to mention is, if we now try to solve for y, is going to be difficult. So I can try to get rid of the y that shows up here in these exponentials by taking the natural log of basically, kind of both sides, and that might kill that off. But it will also introduce a natural log of y that I'll then have to figure out how to undo, that I'll have to undo with an exponential, and I'll get right back where I started. So oftentimes you're going to find that in certain situations, it's not algebraically possible, or at minimum, it's not algebraically convenient or easy to explicitly solve for y. So y is too tangled up here. It shows up both by itself and in an exponential. I can get the y out of the exponentials, but it's going to complicate this y. I can leave this y uncomplicated, but then I still have these complicated exponentials. So there's no way to totally unwind y and solve for y by itself. So we cannot solve for y. in that case, we have to leave our solution like this. This is what's known as an implicit solution. Oftentimes, my preference when I'm dealing with an implicit solution is to at least move everything to one side of the equal sign, except for maybe the constant. And so that's what I'll do here. I would choose, just for the sake of ease, I could write this in, and depending on how you want to, you could try to factor the e to the y term out of these two and write it as a product instead of a difference. Doesn't really make a big difference to me. But what I am going to do is move these two terms over to this side of the equal sign. And again, this is simply a matter of preference. It's not that this way is correct and leaving it as it's written here is incorrect. But oftentimes, this makes it easier to kind of solve for C later on when we do our algebra, if we were to plug in an initial condition. So this is it. This is our solution. This is as good as it's going to get. And again, solutions of this form will absolutely show up. And they're basically solutions where we can't solve explicitly for whatever the dependent variable is, in this case y. They're called implicit solutions. And they're totally valid. Whenever possible, it's always nice to solve for y, but that's not always going to be a possibility. So just keep that in mind. Honestly, this is probably good, but maybe it wouldn't hurt to do one extra example. Let's do one more while we're all sitting here. Might as well. So let's do one last example. One other way you might see the differential equations written, especially in this homework, I don't see this as much in like published research or people that are actually doing stuff in physics and engineering. I don't see this as often, but you may see it with the differential actually split. And what I mean by that is what I'm about to write here. So let's say our differential equation looks like this. Sine of 3x times dx plus 2y cosine cubed of 3x dy. And let's say it's equal to 0. So this is what I mean when I say the derivative is split into two separate differentials. We have dx and dy showing up separately. If I wanted to write it in a similar format to the way that we wrote, for example, this equation up here, where I do have a dy dx, all I would need to do is take this whole thing and divide every single term by dx. If I divide this term by dx, it'll cancel out, but over here I'd get dy over dx. And so basically we're taking some liberties with Leibniz notation here by dividing everything by dx, and we would get back the format that we were accustomed to seeing. So if that makes things easier for you or less scary looking for you, by all means, this is equivalent to starting off with an equation that looks like this. Sine of 3x plus 2y cosine cubed of 3x times dy dx equals 0. So these are equivalent. Okay. In this case, it doesn't make a big difference. It's actually kind of nice sometimes to have it already split for you because it's one less algebraic step that we have over here. I don't have to multiply both sides by the dx to kind of separate things out. So instead, I've got my dx's over here. This term already involves only x's. This term involves some x's as well as some y's. So let's split them up and put them on different sides of the equal sign. So I'm going to keep the, let's say, I guess it doesn't matter too much. Let's keep the sine of 3x dx term on this side, and let's move the term with the y's to the other side. So I'm going to get equals to negative 2y cosine cubed of 3x dy. I've got all the y's over here, but I also have this x term. Let's get this x term over to the other side. How do I do that? I need to divide both sides by cosine cubed of 3x. And so I'll get sine of 3x over cosine cubed of 3x. This is all times the dx term, and on the other side, I'll be left with negative 2y dy. So again, these first few steps are pure algebra, just separating things. Do not make a mistake in the algebra. It'll make everything much, much harder later on. So don't make silly mistakes with the algebra. Okay, so now we can integrate both sides. Again, we wind up with something where one of the sides isn't too bad. This is going to be easy to integrate. But this is a nasty, relatively nasty trig integral. And we're going to need to go back and utilize our skills from Calc 2 to try to evaluate this integral. So this side, when I integrate negative 2y dy, so it's a linear term, right? Y is raised to the first power. I know I'm going to get a y squared. And I know I'm going to have this negative sign that'll persist through the integration. So this side is really going to just wind up being easy. This side is simply negative y squared plus a constant if you want to put the constant on that side. So this side is going to get to be negative y squared plus some constant. That one's easy. But this side is a little bit ugly. So this is a ugly trigonometric integral. So sometimes you might have to sit down and kind of play with this for a few minutes. The way that it's written right now, I can try to do a u substitution involving sines and cosines, recognizing that basically the derivative of cosine is negative sine, and I could try to work everything out that way. That's one approach. I could also recognize that I could write this sine over one of the cosines, right? We have three cosines here. We have a cosine 3x times another cosine 3x times another cosine 3x for a total of cosine cubed 3x. I could take one of those cosine 3x's in the cube and combine it with the sine and get a sine over cosine to get a tangent. And then I'd be left with a 1 over cosine squared. And what is 1 over cosine squared? Or what is 1 over cosine for that matter? 1 over cosine is secant, so I would wind up with a secant squared. So we can convert this to secants and tangents if we want, or we could try to do it with sines and cosines. It's kind of up to you, depending on what you're more comfortable with. In this case, I'm actually going to do, I think I am going to switch this to be tangents and secants combined. So I'm going to, it's normally not what I do. Normally I like to leave things in terms of sine and cosine whenever possible, but this is one where I don't think it'll be too bad. So it's kind of up to us. What the heck? Let's do it with sines and cosines. I think that would probably be most people's approach. So we have multiple approaches. Let me just write that. So I could do approach 1 is just write this as, keep it as sine of 3x over cosine cubed of 3x dx, and let our u be equal to, so do u substitution, let u be equal to the cosine of 3x, which tells me that du, the derivative, is going to be, what's the derivative of cosine? It's negative sine, so I'd get sine of 3x, I'd pick up an extra factor of 3, and I'd have a negative symbol there, times my dx. That would be one approach. A second approach, which I'll write down here, is I could write this as sine of 3x over a cosine of 3x times 1 over a cosine squared of 3x dx. That can be rewritten, this sine over cosine, as a tangent. So I'm going to get tangent of 3x times, in this case, 1 over cosine squared is times a secant squared of 3x dx. And this isn't too bad if you recognize that what is the derivative of tangent? The derivative of tangent is secant squared, and so you could do a simple u substitution here to do this one. So it's kind of up to you which approach looks easier to you. You will get slightly different looking answers. They will be technically algebraically equivalent, but the algebra sometimes is kind of nasty to convert between the two answers that we might get, even though they are indeed going to be equivalent. Okay, so honestly, this one's looking easier to me now that I have it written out. But let's do the first one instead for the time being. So okay, so for my du, I've got -3 sine of 3x dx. I have a sine of 3x dx sitting here, but I don't have the -3 that I might want. So I'm going to put that -3 there, and I'm going to account for that by also putting a -1/3 out in front of everything to cancel it. And now I get something that looks like I've got that -1/3 out in front of everything times the integral of, well, now I have -3 sine of 3x on top times my dx, so I have du on top. And on the bottom, I've got cosine cubed of 3x, but u is equal to cosine of 3x, so on the bottom I simply have u cubed. And so when I integrate this, you can think of this as simply being u to the -3rd power. So I've got -1/3 times the integral of u to the -3 power du. The power will go increase by 1 when we integrate, so it'll go from u to the -3rd power to u to the -2nd power. So we'll get, still got my -1/3 out in front. I'll get u to the -2nd power. And we just need to remember now, again, if I were to take a derivative, I'd get a factor of -2 here that I don't necessarily want. So I'm going to put a -1/2 as well. And I've got my plus c, but did I already account for my plus c up here? Okay, good. I already put my plus c here, so I don't need it again down here. And it looks like, what do I get? 1/6 u to the -2, where u is that cosine term. So this is going to be 1/6 of cosine 3x, cosine squared of 3x. But it's negative, so that whole thing is in the denominator as well. So maybe I can clean that up a little bit and write it as, put the 6 down there and do the 1 there. Okay, so the other approach is integrating this function, which is the integral of tangent 3x times secant squared of 3x dx. And we actually even have two approaches for this. I can choose for my u to be the tangent of 3x term, and my du, the derivative of tangent of 3x, is going to involve a secant squared. The derivative of tangent is secant squared. Or I could pick out one of the secants here and be left with a secant tangent, and the derivative of secant is secant tangent. And I can take either of those approaches. Let me do the one that involves letting tangent be our u. So I could let u be equal to tangent of 3x. And that means that my du is going to be the derivative of that. So the derivative of tangent is secant squared. So this would be a secant squared of 3x dx. But I'm also going to pick up by chain rule a factor of 3 in there. And so in this case, if I come back to the equation over here and kind of rewrite things, I've got my u sitting right here. Here's u, here it is. And I've almost got my du. I've got secant squared of 3x dx, but over here I have 3 secant squared of x dx. So I'm going to sneak a 3 in here and make up for that with a factor of 1/3 in front of the whole thing. And so what I'll get in that case is I've got my, let me just write it all kind of a little bit more cleanly. In this case, I've got that 1/3 times the integral of my tangent of 3x, which is u, times 3 secant squared of 3x dx, which is the same as 3 secant squared 3x dx, same as my du. And when I do that, we can integrate u du, no problem. I'll have my 1/3 out in front of everything, and I'm going to get 1/2 u squared when I integrate the u term, and I'll be left with 1/6 u squared, which, plugging back in for what u is, it's this tangent of 3x term. I'm going to get 1/6 tangent squared of 3x. And if I look at these two answers, they look a bit different. And indeed, they are a bit different. I can rewrite this one a little bit. I can pull that 1/6 out and write this 1 over the cosine squared as a secant, so I could rewrite this one as secant squared of 3x. But notice these two things are still not the same. 1/6 secant squared of 3x is different from 1/6 tangent squared of 3x. But the question is, how do they differ? These two things, even though they look different, and it's like, okay, maybe we screwed up, we didn't screw up. These two solutions differ by a constant. And if you remember your Pythagorean theorems or your Pythagorean identities from trigonometry, the simple one is that sine squared of x plus cosine squared of x equals 1. But if I divide both sides of this, or the whole thing rather, by cosine squared, then this whole thing becomes tangent squared of x plus 1 equals secant squared of x. And that's essentially the argument I'm making here. We just have a factor of a sixth in front of both of them, and instead of x, it's 3x. But the same argument. I could relate these two things to each other using the Pythagorean identity that looks like this, and you'll notice that they just differ by a constant. But they're allowed to differ by a constant because we have an unknown constant of integration. If I use this as my answer, and then plug in some initial condition to find c, I'll get a different c than if I use this as my answer and plug in that same initial condition to find c. So they're equivalent, they differ by a constant, but we're allowed to have our solutions differ by a constant because we have an unknown constant of integration in both of these terms, right? We left off the plus c in both of these cases because we'd already accounted for the plus c over here. So hopefully that makes some sense. The answers look different. At first glance, you might think that there was some mistake made, but the reality is the answers are allowed to be different as long as they only differ by a constant, because we can account for that with our constant of integration. So we're in good shape either way. So depending on which one of these you want to use, it doesn't matter to me. I'll use the second one just because I like tangent a little bit more than secant, I guess. We have our answer for this piece, and our solution is, so we get, on the left-hand side, I get 1/6 tangent squared of 3x, and on the right I get equal to negative y squared plus c. Okay, just wanted to zoom out so I could see it all at once. So here's our solution. Can we solve for y? Yes, we can. It's going to make this look a little bit ugly, so this is probably fine, but if we wanted to solve for y, it wouldn't be too bad. We'll just subtract c from both sides, multiply by -1 to get rid of this negative sign, and then take the square root, essentially. So that's what we would wind up with. So if we solve for y, which is doable, I'll get 1/6 tangent squared of 3x minus that same constant c is equal to negative y squared. Get rid of the negative sign, and I'll wind up with c minus 1/6 tangent squared of 3x, so flip the signs of basically both of these terms, is equal to the y squared. And to get y by itself, we will get that y is equal to the square root, and there's two possibilities, plus or minus square root of c minus 1/6 tangent squared of 3x. And there's what our solution to the original differential equation looks like, solved explicitly for y. And again, if we wanted to plug in an initial condition, we would do that in this final stage here to figure out what value of c works for the specific point that we're trying to satisfy, or the specific condition that we're trying to satisfy. So that's one more example. Try some of these on your own. I think you'll start to get the hang of them. Honestly, again, the differential equation portion of this is just, can you do a bunch of algebra, and do you remember your integrals from Calculus 2, basically. So let me know if you have any questions, and good luck.